Plaisir d'accueillir Stephane Aicardi, que vous connaissez tous pour ses activités responsables de la DIO dans le dernier mandat. Donc, je ne dis pas grand-chose, hein, Stéphane, mais juste pour rappeler que Stéphane a une formation de mathématicien et qu'il travaille en ce moment sur des réseaux de neurones convolutifs, des CNN, dans le cadre du projet Minerva, en particulier avec Baptiste Secconi et puis des gens qui font de la planéto sur des données radio de la station de Nancy. Et voilà, il va nous en dire un petit peu plus aujourd'hui. Merci beaucoup, Stéphane. Je te laisse la parole et on va passer en anglais là, probablement. Voilà, merci.
Merci, Philippe. Donc, c'est normal, je le remets. Hello, thank you for this opportunity to present my work. In this talk, I will briefly describe jovian decametric emissions. Then I'll do some reminders on deep learning techniques, and I'll apply those techniques to the jovian emissions observed by the Nancy decametric array. First, I would like to thank Baptiste Secconi, Laurent Lamy et Philippe Zarka in the Lysia department. I will present some work from Corentin Louis. I will use a huge work from Manila Marquez, which I'll present further. And I will present something that uses a portal built by Mathieu Servilla, which is here. Hello, Mathieu. This work is obviously funded on lots of research in machine learning, so I didn't have the space to cite them all. And I'll thank Minerva for its support and its beautiful hardware. So, what are jovian decametric emissions? In the 50s, the first radio telescope in the decametric array have spotted that Jupiter emits lots of radiations, and those emissions are now understood as produced by the cyclotron maser instability, which is due to the solar wind or due to Jupiter and Io electrodynamic interaction. Here, hope you see my pointer. We have a sketch that presents all the cases that we'll use later. So we have either IO or non-IO emissions. They come from particles that go to the northern pole or the southern pole. When they go to the northern pole, they are right polarized. To the southern pole, we get left-handed polarization. And if they are in the downside, we see emissions that's curved this way, and the dusk side they are turned this way. It's because of the rotation of Jupiter and the satellites. Here I plot the probability of occurrence of those emissions with respect of the longitude of Jupiter in its rotation and the phase of Io. We see big peaks of probability of emissions linked to Io, which are A, C, B, and D. And we see also those diffuse emissions here, which are not related to Io. Here are the non-IO-A, non-IO-C, non-IO-B, and D around there. The Nancy decameter array has been built in the 70s, and it uses a numerical receptor since 1990. It observes daily the Sun and Jupiter. We have now 3 main receivers for Jupiter. One that is routine, which is low resolution. We have 2 channels, left and right polarization. Each channel is sampled every second, and we have 400 slices in the frequencies. So it's a very moderate size of data each day. But if we take the Juno N receiver, it can go to up to 3 terabytes per day, which is obviously huge and difficult to store in the long run. So we need a way to choose if we need to keep those high resolutions data, and this work is a way to achieve this. Here are some typical emissions. We have here IO emissions. On single observation, we have here a IO-A emission, here IO-C emissions, and we see here we can see the counterpart of the IO-C emission in the right-handed polarization. Here there are IO-B and D here. And here are non-IO decametric emissions, non-IO A, B, C, and D. So those emissions are, for an expert, they can be identified by the eye. But we want to see if we correctly understand the mechanic of the production. So Corentin Louis has built a simulator of those phenomena. Here we can see a good accordance between the simulation here and the observation. This work, this simulator is a part of the Maser project. And here we can see the portal, which allows everybody to run on demand some simulations using this program. This portal is using the Opus server built by Mathieu Servilla. Now I will talk about neural networks and deep learning. So what are we trying to do with this? We can try to classify data. So as soon as we try to classify something, the first example is to classify cats and dogs, hence the cat picture. We can then try to localize some objects of interest in a picture. So here we have bounding boxes, and within those boxes we have the type of the object and the probability of the confidence that it's really that object. Furthermore, we can try to segment the image, that is to replace the image with false colors. Here we have the color for the road, the car, in red, the people, the street signs, the trees, and the sky. We can also try to generate data that look like our training set. Here is a fake celebrity that was produced by NVIDIA using a data set of celebrities. We can also try to translate text from one language to another. There is DeepL. It's an online service that does exactly this. And networks can also play games and even beat the best players in the best human players in the world. Here is the example of Go, which was where AlphaGo beat in 2016 the best player. How do they work? So in the 50s, there were people built the Perceptron, which was a way to mimic the biological network. So we have some inputs. We have weights, which are the parameters that we want to train to obtain our results. We multiply the weights by the inputs and we sum everything. The result passes through a step function and we get our output. So with this simple process, we can model some mathematical functions. So that's a good start. But soon people realized that very simple functions as the XOR couldn't be obtained this way. So there was a halt on this concept. But it came again in the 80s because one neuron doesn't do much and the brain contains billions of them. So somebody found an algorithm called the backpropagation, which allows us to train multi-layer perceptrons. So each circle here is a perceptron like this, and we chain them and build them into layers to obtain our result. So this model works correctly on small inputs, but if we add lots of layers, we will have a number of parameters which will grow too fast. So to avoid this problem, Yann Lequin invented the convolutional neural network, which shares the weights between lots of neurons. This way, we have less parameters to train, but also we have something that's better suited for to handle the symmetries of the problem. For example, when we want to detect something that's slightly left or slightly over where we expect it, it works the same way. To handle time series, people developed the recurrent neural network that where the output is fed as an input on the next stage. We have many architectures for this, notably the LSTM, long short-term memory. To generate data, we have the generative adversarial network, which is built on the concept of the police and thieves. the thief want to make fake banknotes, and the police want to know if a banknote is real or fake. So we train both models, the one that generates and the one who discriminates, and that's this way that we can obtain that kind of photo. And last, I want to to present a UNet, which is first an encoder that takes an image in input and finds a small representation of it. Then it expands it to get either the same thing at the input, or something like these images there, where we colorize the elements of interest. So that's the main tool for segmentation. Next, small focus on the convolutional networks. First, Yann Lequin produced, a small convolutional network to classify. In fact, he wanted to read the numbers on checks, which were handwritten, and he managed to recognize it with a very small convolutional network, because the input was only 28 by 28. But it was okay for its purpose, but it couldn't be really generalized to bigger data, because the computers of this time couldn't handle this kind of computation. So we have a big gap until 2012, where AlexNet was the winner of the ImageNet annual contest for to classify images, and he managed to do this with a convolutional neural network, and his score was twice the other people score, which was a huge gap. So in the next years, all the other techniques to classify images were gone, and people used only convolutional network and were optimizing them. In 2014, we have two competitors, VGG, which is what I would call a vanilla convolutional network. It uses only kernel of 3x3, and we have convolutional pooling, convolutional pooling, and last classification. On the other hand, GoogleNet used a very complicated module, which uses many paths with different sizes to try to get some to identify features. With these two concepts, it was clear that it could be interesting to build deeper networks, but if a network was too deep, we had the problem with the vanishing gradient. So people tried to find a way to fix this, and first is ResNet that uses some skip connections to avoid this vanishing gradient. Then DenseNet does essentially the same thing, but a little more complicated and with less parameters. And last example, we have MobileNet, which tries to do very tiny convolutions in order to have a model that fits on a mobile phone. So since, I would say, 10 years, we got many trends. One is to build deeper networks with ResNet and DenseNet. One that is to build wider networks. I mean by that, networks with lots of features. We have wide ResNet, ResNext. Then the other path is to build smaller networks because they are smaller. They can run faster, train faster. And the last trend is, in fact, not to be a smart guy when building the architecture, but using learning techniques to find the better one. And the best in this case is EfficientNet. Here is some performance evolution. So first, AlexNet, we have lots of parameters, not so many flops, and a result that that was marvelous at the time, but it's really way behind what we can do now. If we compare GoogleNet and VGG, we can see that VGG is really huge in terms of parameters and in flops. And we have around the same performance. With ResNet, which is much deeper, we can use less parameters for flops to achieve a better performance. Same with DenseNet, but slightly better. With MobileNet, we can see that we have around the same performance as VGG, but with way less parameters and flops. And with slightly more parameters, EfficientNet can do much better. And EfficientNet exists in many sizes. So B0 is the smallest one. It can grow to B7, which I didn't put here, which is quite huge, but is way smaller than its concurrents. What I want to show here is that there's been a lot of research in this domain, and all these networks are available with their weights. So we can use them directly in our code, even if we don't want to classify cats and dogs, but for example, Jupiter decametric emissions. And using them speeds up training very drastically. So now I will talk about what I tried to do with the decametric emissions of Jupiter. First, let me show the data well, without any treatment, as they come from the receiver. So we see about nothing except those stripes here, those stripes here, and there it is. In fact, here, those are the calibrations of the array. Those here are the RFIs, so CB, military device, and so on. We have even some saturations, while the output of the receiver is an integer between 0 and 255, and when the data is over 255, it goes back to 0, and that's what we see here. And if you look closely, here is the data of interest. So it's it seems to be really hidden in the dynamic. Now let me present the catalog, which was built by Manilo Marquez. It used the 20 years of observation by the Nancy decametric array with the routine receiver. So you have lots of observation, lots of emission, and for each emission, he noted the type of the emission, the polarization, the time range, and he drew a polygon over each emission. So I use this polygon here to represent a data. That's one sample where we see lots of different emissions here, IO A, and then lots of non-IO emissions. So first of all, I tried to classify the observation. So for this, I used samples that contained only one type of emission, and I used them to train a convolutional network. With that, I obtained 80% of correct classifications, which is not bad. Well, it tells me that that's something that's working, but it's not marvelous. If I use as input the jovian satellites ephemerides, then I grow to 88% of correct classifications. That's because in the first classification, I saw that lots of non-IO was mistaken for IO emissions and vice versa. With this, I thought that's promising results, but that can't be the end of the story, because we have lots of cases where simultaneous emissions happen. And we can't treat simultaneous emission with this kind of network. So I decided to try the segmentation case, which is in fact that I want to reconstruct those polygons from the observation. For this, I cut samples of 400 seconds into observations. Why these 400 seconds? It's because most of the emissions are in a time range of about an hour. Then I clean the calibrations, the background, and the filters that I used. I normalize the data in mean and sigma. That's because the scientific data is usually about 1 sigma above the mean, whereas the RFIs can be 6 or more sigmas above the mean. So the idea is to change the dynamic of the input to help the network. Then I reduced the samples to something that computer can handle, because 4,000 for one side would be too big. And I obtain samples that are 400 by 400 by 3, which can be handled by lots of convolutional network. My input is a segmentation into 9 types. So it's either nothing, IO A, B, C, and D, or non-IO A, B, C, and D. And I reduced to 100 by 100 because of the size of the network. In the end, I obtained a big training set and 2,000 samples in the validation set. Those two sets are balanced with respect for the presence of emission. That means that I have as much samples with an emission that I have samples without an emission. Now, how do I treat them? Well, I use essentially a unit architecture. I use EfficientNet trained with ImageNet as an encoder, and I use a simple convolutional decoder. So here is my input that goes into the encoder. I obtain a latent representation of the latent representation from EfficientNet. I add the ephemerides at this stage. Then it's used to feed a fully connected layer to obtain the detection. So it's binary. There is something or there is nothing. And also use this latent representation with the ephemerides into the decoder to obtain the segmentation. Here are the number of parameters, and most of the parameters are in the decoder, which I think it's a place to optimize. And here are the results. So I obtain more than 97% of success in detecting the presence of an emission. And on the segmentation, I obtain 93% of intersection over union. That seems great, but if the nothing part of the segmentation is raising this number. So it's in the end, that's not exactly what we think it is. Anyway, here is the results of the network that we can compare to the manual catalog. So we see a good occurrence, but here we have some things missing. Here it's a bit skinny, and here, so here is a probability to have an emission just over, and here we have a peak, which, according to BASIS, could be here a non-IOB emission that was missed by Manilo Marquez. So to visualize this, I built a small web portal, which I will show you. So I can look at the catalog or at the predictions. So here I can compare to the catalog. It's very fast because it's already calculated. So here is the catalog. Here is the prediction, and if I reduce a little the resolution, we can see both at the same time. And I get the list of emissions that were detected, and if the temporal localization is correct, and here the IOU is calculated without the background, so only on the emissions. So it's much lower than what I said before, but to the eye, it's already satisfying. And then no, it's the same. I can also use, let me grow it a little. I can also predict, use this network to predict what can be seen on the latest data. And if I go to the end, I get this one from yesterday, and we see nothing. So it's not really interesting. And if we look just the day before, hello, yes, here we can see that it detected IOR. So now we would like to know if these predictions can be correct. And for this, I created another website which will look at the ephemerides to check if there is a good probability of having a IOA or not. And let me show you, not this one. Okay, so it's here. I can select the observatory, but it's Nancy, obviously. I can I can copy and paste. Sorry. I can copy and paste the dates. I can select the satellite that I'm interested in. Here it's Io. And I can choose lots of background map. And here is the result. So we see the trajectory from the Jupiter in this diagram. Here we have the CML, that's the longitude of Jupiter, and here the phase of Io. And we see that at some point, Jupiter should be in the range of IOA, and that's exactly what my model predicted. So that seems fine. And next, sorry, here I have the simulation done with Express to compare. See that the Express tells us that the IOA should be around 10, 11, but we observe it we're around 10, that's in the 2 error range of error of express, so that's okay. And then we can also try to see if it's a link to Ganymede. Here we can see that obviously it shouldn't be the case because it's outside all the boxes. And so the next stage would be to apply this work to emissions due to Ganymede and maybe Europa. For Ganymede, we have strong statistical evidence for emissions in the link to Ganymede here. It should be Ganymede B, A, C, and here maybe D, but that's not significant. Here in with Europa, we can see that's only the thousands emissions. We can see that there should be some Europa C data here, but it has to be confirmed. Other perspective, would like to reduce the decoder parameters in my neural network to speed up training and inferring. Obviously, we'll need more validations. And one of the objectives is to build a TAP service with the original catalog from Melio Marquez, and also the automated predictions. And this catalog would use Baptiste Cicconi's TF-CAT, which will describe polygon in the time frequency domain. And another use of this work would be to detect emissions in real time and use it to signal other services which could this signal could be used to keep high resolutions observations or to point observatories to the to Jupiter to observe more carefully. And that's it. Thank you for your attention. And if you have questions, maybe I'll try to answer.
Thank you, Stéphane. So question, Antoine. Hello, it's not a question, just a clap.
Yeah, sorry, it's just a clap.
I have a question.
Yes, Philippe.
Hello, Stéphane.
Hello.
When you compare the result from the algorithm and the manual or visual recognition, why don't you do just AND and XOR the two images, the two contours, and the two boxes, so that you see which part are indeed recognized identically, which part are not, and it would be more precise than just comparing qualitatively.
So in fact, that's what the IOU does. It's IOU. It's intersection over union. So you calculate the intersection of the prediction and the catalog data. You calculate the union of the same, and with this this ratio, you can know if it really fits, if it's 100%, or if it's completely wrong, where you'll have 0.
Okay, no, I understand, but what I said was just that you can plot actually
Yes, okay. Yes, I can.
So you can see on the dynamic spectra what fits, what doesn't fit. But it's okay. I mean, it's just a small suggestion.
Okay, we'll try.
I have a question related to that as well. I mean, when you showed, I think you showed one emission, which was, you said that Baptiste said that it might be a real emission.
Yes.
So it means that in fact, the label was not done correctly. So it didn't learn correctly how to recognize this. Is there a way to identify those kinds of bad identification due to bad labeling? I mean, do you have a class of objects for which I don't know, the probability is maybe average, or there is something which is in the middle, which could trace something which might be due to bad labeling?
So it's hard because the way this work is done, I consider that the catalog is the Bible. It's always right, and that's the way it is. Nevertheless, so this the algorithm can indeed point out some places where the labeling could have been wrong. In this case, I would say that we need to look at them, at least the most serious ones. That would be with the largest probability. To see if experts can validate those cases. In this case, they would be added to the ground truth of the catalog.
Yeah, like Jupyter Zoo, where you could.
Yeah, yes, indeed. I think that in the end, it could be something like this.
And I had another question about the ephemeris. I'm not sure I understood the point. You expect the emission to be there related to some positions. Is this correct?
Yes.
So in fact, there is one more. So in fact, there is one more information you give to the network, which is not a labeling, but it's also it's the ephemeris. Am I correct?
Yes. So in fact, I tried. I always try both with and without the ephemeris. Okay. I think it's interesting to see if the network can really identify the emissions without this information. But obviously, this information is important, and this information was used by Manilo Marquez to build this catalog.
No.
No?
It's very important. This information was actually, I'm a co-author of this paper. That's why I know the content. No, it's precisely, it's explained at the beginning of the paper. The information about the ephemeris was not used because, but only the morphology, the polarization, the shape.
Okay. I misread.
Just because if you use this information, you have it's very difficult to detect, for example, emission by or controlled by other satellites or things like this. You have an a priori on that. So we try not to use this.
Okay.
Other questions? I had a more general question about the units again.
Yes.
I remember we talked about the fact that you could train the unit. I mean, the unit without the flagging. Is there a way to do some segmentation without a priori information, without any catalog, to separate the shapes? For instance, to remove the parasites or such things like that.
Well, what we can do with a unit without any information is a autoencoder. So we just build a network to reconstruct itself. and the result of this network will be, in fact, the representation, the latent space. And if we do it correctly, we can then try to find in this latent space information by clustering to find maybe some useful information. And it's something that that can look like PCA.
So can you do something like classification in the latent space?
And yes, you can do clustering in the latent space if you build it correctly. I didn't do this, but I saw this in some papers. You can do this if you tweak your learning algorithm correctly. You'll have something that's more or less continuous. That is that in the latent space, two representations of similar data should be close, and so by clustering you can do a proto classification. But I'm not absolutely not sure that just like I did here, it would work from scratch.
Okay, and in such a case, you need to give the network relative importance of similar images, so that you can recognize or classify in the same latent projection the different features.
Yes, in fact, that's also why I use so much data without any emission. It's I think it's really useful to so that the network learns how the airfiles can look like, so it can learn to discard them and extract only the scientific data.
Okay, thank you. So I don't know if there is any more questions. It's almost an hour, so thank you very much, everybody. Thank you again, Stephane.
Thank you.
And see you next week then.